Welcome to today's Explainer. We're jumping right into the fascinating, totally invisible safety nets that battle network chaos every single millisecond, just to deliver perfect information right to your screens. We're talking about the foundations of data transmission error detection. And look, I know that sounds highly technical, but I promise you, it's actually the unsung hero of our entire digital lives.
So think about this for a second. How does your computer actually know a file isn't corrupted? When you download a massive, high-definition movie or, send a really crucial work email, that data takes a pretty perilous journey across copper cables, fiber optic networks, and wireless frequencies. Every single 0 and 1 is at risk of being scrambled along the way. So how on earth does the receiving device know that what it finally got is exactly what was originally sent?
Okay, let's dive into this. Here is our roadmap for understanding it all. First, when data goes wrong. Second, detecting transmission errors. Third, guaranteeing safe delivery. And finally, catching data entry errors.
Part 1. When data goes wrong.
The absolute villain of our story here is interference. These are disruptions during transmission that actively cause errors. As these fragile little data packages travel across local and global networks, interference is just constantly working against them. They're battling electrical noise from power lines, signal degradation over long distances, or honestly, even just a microwave turning on nearby and completely messing with your Wi-Fi signal. Because of all this constant chaos, things go wrong very fast. Transmission errors caused by interference happen in three main ways. First up, data loss. This is where bits of information simply vanish into thin air during the trip. Second is data gain, where random, totally unwanted bits of data just get shoved into our clean data stream out of absolutely nowhere. And third, data change. This is when a 0 gets accidentally flipped to a 1 or a 1 flipped to a 0. The package arrives, sure, but its fundamental meaning has been completely altered.
All right, moving to part 2, detecting transmission errors.
Let's slow down a bit and meet the heroes of our story. Our first line of defense is the parity check, which basically adds an extra bodyguard byte to the data. This comes in two flavors, odd parity and even parity. In even parity, the total number of 1 bits must always add up to an even number. In odd parity, you guessed it, the total has to be odd. If interference flips even a single bit during transmission, that final count is going to be off, and the receiving computer instantly flags the data as corrupted. Now, what's really interesting about this is that we can level the concept up into a parity block check. Instead of checking just 1 byte on its own, the data is arranged into a grid. Parity bits are then calculated for entire rows and entire columns. By tallying the bits both horizontally and vertically, it's like a giant puzzle. If a single bit gets flipped by interference, the intersection of the failed row and the failed column pinpoints the exact specific location of the error. Another incredibly elegant method is the checksum. Think of this as a mathematical receipt for your data. Before transmitting anything, the sender runs all the data through an algorithm to generate a very specific mathematical value. This checksum value is sent right alongside the data. When the receiver gets the package, it mathematically recalculates everything on its own. If its final total matches the sender's checksum perfectly, the data is safe. If not, an error definitely happens somewhere in transit.
And then we have the echo check. This one is remarkably simple but highly effective. Step 1, the sender transmits the data. Step 2, the receiver simply echoes or throws that exact data right back to the sender. Step 3, the sender does a direct side-by-side comparison. If what it originally sent matches exactly what just bounced back, boom, the transmission was a success. It is quite literally the computer equivalent of asking, "Hey, did you hear what I just said? Repeat it back to me."
Which brings us to part 3, guaranteeing safe delivery. So what actually happens when one of those frontline defenders finds a problem? Enter the Automatic Repeat Query, or ARQ. This is the ultimate delivery guarantee protocol. ARQ is a system used to definitively establish that data is received without error. If a parity check or a checksum flags that interference has ruined the data, ARQ is the automated mechanism that steps right in to make sure those corrupted packages are entirely replaced.
To pull this off, ARQ relies heavily on feedback, specifically positive and negative acknowledgments. A positive acknowledgement is a message from the receiver basically saying, "Got the data, ran the checks, everything arrived perfectly." A negative acknowledgement is the receiver saying, "Okay, the data arrived, but the parity check failed. It is completely corrupted." That negative acknowledgement immediately triggers the sender's network to resend the bad data. So this builds into a complete, logical ARQ sequence. Step 1, send the data. Step 2. Instantly start a timeout clock. Step 3. Wait to receive an acknowledgement. Step 4. Resend if needed. But here's the critical question. What happens if the data gets completely lost along the way and never arrives at all? The receiver can't send a negative acknowledgement for something it didn't even know was coming. That's exactly where the brilliant timeout concept shines. If the sender's timeout clock runs out before hearing any reply whatsoever, it just assumes the data vanished and resends it automatically.
Finally, Part 4. Catching data entry errors.
Let's step away from network cables for a second, because humans are flawed. We make typos, we fat finger keys, we transpose numbers all the time. To combat this before the data even hits the wire, we use the check digit. This is a specialized hero, an extra number appended to a string of digits specifically designed to detect our clumsy human mistakes and protect the data's integrity from the get-go.
And this brilliantly illustrates the concept. Take a standard International Standard Book Number, or ISBN. When a librarian or a bookstore clerk types this long string into a system, they could easily mess up just one digit. But that final number, the 2 at the very end of the sequence, acts as the check digit. The computer instantly runs a mathematical formula on all the preceding digits, and the answer absolutely must equal that final check digit to validate the whole sequence. If the clerk typed it wrong, the math simply won't match, and the system totally rejects the entry.
The crucial takeaway here is that this isn't just theoretical computer science. You rely on check digits every single day. The most common everyday uses are in those ISBNs we just talked about, and in standard grocery store barcodes. When you're at the store and the cashier scans your item, the reason that scanner happily beeps is because the internal system just instantly verified the check digit mathematically. It guarantees the correct item is being rung up, catching scanner errors or misprints in real time.
So, what does this all mean for us? We've explored the absolute chaos of interference, the mathematical elegance of parity checks and checksums, the relentless persistence of ARQs, and the everyday cleverness of check digits. So, the next time you scan a barcode at the store or successfully download a massive file, will you think about the invisible safety nets making it happen? The digital world is inherently chaotic, but thanks to these foundational error detection methods, our information arrives exactly as it should. Thanks for exploring this topic with me. Keep asking great questions, and I'll catch you in the next explainer.